Hello people, now we need to see a couple of things regarding echelon form and reduced echelon form. Those will be useful now when we solve linear systems. That will tell us pretty much when we need to stop. We need to stop when we reach reduced echelon form, and also later on it will be useful for some other things. We start with definitions, and what you want to see here is that sometimes things can be cryptic. So let's start with the definition of a matrix that is in echelon form. Obviously we talk about row echelon form, but since we are talking about rows all the time, so we just drop the row part. So we say echelon form of a matrix. So if we have a matrix that is in echelon form, then what we say is that all of these three properties are true at the same time. So what are the properties? All three of them need to be true for the matrix to be in echelon form. So no matter the order we start. So the first one says all non-zero rows are above any rows of all zeros. So translation from Chinese, it means that if you have a row of zeros, it should be at the bottom. If you have two rows of zeros, they should be at the bottom. If you have three rows of the zeros, they should be at the bottom of the matrix. That's what it means. Second condition, each leading entry of a row is in a column to the right of the leading entry over the row above it. Okay. Translation from Chinese, these leading entries, those are leading entries any number different from zero. Okay, so if you have a row, you find the first number that is different from zero in that row. Beautiful, that's your leading entry. You go to the next row and you check what's the first non-zero entry in that row. Well, what they require here is that the leading entry from the second row needs to be to the right of the previous leading entry. So basically you have some type of a staircase. We will see that illustrated properly. It's not so clear here. The last one, it says all entries in a column below a leading entry are zeros. Okay, so you have your leading entry and you look below the leading entry. What you need to see is all zeros. All entries are zero. So when you have a matrix that satisfies all of these three conditions, then that matrix is in echelon form. Beautiful. Reduced echelon form? Well, if a matrix is to be in reduced echelon form, it obviously first needs to be in echelon form. So the previous three conditions need to be true. Now we add two extra conditions. Because it's reduced, it's something much more special. One of the conditions says the leading entry in each non-zero row is 1. So your leading entries need to be 1. Okay, cool. Each leading entry is the only non-zero entry in its own column. Aha. So my leading entries need to be 1, and when I look at the column containing the leading entry, well, all I see is 0, 0 everywhere, except at the leading entry, which is 1. Very nice, easy. So let's see some examples to actually figure this out. So we start with example here, the first matrix in the left corner. So I hit the row, first row, I have my leading entry is 3. Beautiful, I have my leading entry, let's identify it. My leading entry 3, gorgeous. I'm done with the first row. Second row, I hit the second row and go find the leading entry of the second row is here. So let's put the square just to see it. So my leading entry of the second row is to the right of the leading entry of the first row. Great. Let's hit the third row. I check. Oh, the first non-zero entry. It's here. Okay. Great. So now I see that my leading entries any number different from 0, are to the right of each other. So they go in a cascade, in some type of a staircase. See? We start here, and then it goes up, and then here, it goes here, So we have some type of a staircase. Okay, good. So leading entries are to the right of each other. Beautiful. I don't have any row of zeros only. That's good. So fine, no problem. If there is, then it should be at the bottom. But here there's no problem with row of zeros. Now, the last condition was for echelon form was that below my leading entry in that column I have zeros. That's true here. Beautiful. This column, the second column, is also called pivot column because the leading entry in some book they call it pivot. So pivot column doesn't matter. And then I have the leading entry here. Below I have zeros. Great. And then I have leading entry and nothing below. Fine. So actually I have the conditions satisfied for echelon form in this matrix. So this matrix is in echelon form. Great. Let's change the matrix. This one, second one in the middle. First row, pop, leading entry is -2. Let's put the square around -2. Okay, I hit the second row. Leading entry is 5. And it is to the right, oops, it is to the right of, okay, it is to the right of 2. Okay, that's good, good news. Now, third row, I have my leading entry. Leading entry is 3. It is to the right of the previous one. So all good. I don't have any rows of zeros only. That's fine. So no problem at all. So now I check my leading entry, -2, and I check the column that he belongs to. And below him, I have only zeros. Great. Below this leading entry, only zeros. Below this leading entry, nothing. All good. So I'm all clear. This is echelon form. By the way, it's not in reduced echelon form because my leading entries are not 1. That's one of the reasons. Second reason, to be in reduced echelon form, your leading entry needs to be the only non-zero in its column. And your leading entry needs to be 1. So obviously I don't satisfy those two conditions. So this matrix is in echelon form. This one here, well, leading entry is here for the row 1. For the row 2, leading entry is to the right. Great, no rows of zeros. My leading entry below him in the column are all zeros. Great. No problem at all. Let's see this one here. So my first leading entry, 9. Great. And then the row 2, the leading entry is to the right. Great. Row 3, leading entry is to the right. So zeros are not leading entries. Anything different from 0 is a leading entry. And the last row, it's all zeros. I have a row of zeros and it's at the bottom. Good news. So I have my leading entries to the right of each other. And row of zeros is at the bottom. Great. And the last condition I need to check. This is my leading entry in its column. Everything is 0 below him. This is my leading entry in its column. Everything below is 0. So that's good. Leading entry below 0. Great. So this matrix is in echelon form. What do we see here? A column of zeros. Do we care about it? No. We are concerned about rows. We don't care if we have a column of 0. Nobody cares. This matrix, again, I have my staircase. You see it there. So my leading entries are to the right of each other. That's great. No row of zeros. Good news. So my leading entry, I check its column. Below him, all zeros. Great. Leading entry, below him, all zeros. Great. Leading entry, below him, all zeros. Great. Leading entry, nothing below. All good. So this matrix is in echelon form. This one too, for the same reasons. This one also. And what happens here? Well, I have my leading entry 7, and then 3, and then 2, and then 1. That's it. So I have my staircase, so my leading entries are to the right of each other. That's super important. I happen to have also a row of zeros, which is at the bottom. Great news, that's what we need. And then I check the columns containing my leading entries, the pivot columns. So below my first leading entry, 7, I check all zeros, all good. My next leading entry is 3. In his column below him, all zeros. Next leading entry, 2. Below him, all zeros. Next leading entry is 1. Below him, all zeros. Great, this matrix is in echelon form. What happens with the column 2? Nothing. Nobody cares about column. What happens to this column? Nothing, we don't care. What happens to this column? Nothing, we don't care. We care only about columns to check for the zeros that contain leading entries. What happens to the column that doesn't have a leading entry? Well, nobody cares. Alright? So now some examples of a reduced echelon form. So this is where special matrix is. So this one, first leading entry is here. And then the next is to the right, and the next is to the right. So that's first thing, good thing. All my leading entries are to the right of each other. No row of zeros only, great. No row of zeros, no problem. I have a column of zeros. Nobody cares about columns. Definition doesn't talk about columns, just about rows. Now I have my leading entry, and I have 0 below. That's good news. Leading entry, 0 below. Leading entry, nothing below. Okay, good. So up to now, I have 3 conditions satisfied. This matrix is in echelon form for sure. Echelon form guaranteed. Let's see if we meet the other 2 requirements to be in a reduced echelon form, like special price. My leading entry, 1. Another leading entry, 1. Another leading entry, 1. Wow, great news. We have 1 more condition satisfied. Last condition says your leading entry is the only, so it's 1, and it's only non-zero value in its own column. Here that's true, because in his column he's on the top and then below all zeros. This guy, leading 1, in his column, well, above him zeros, below him zeros. Great. This leading 1, in his column, above him zeros, below him nothing. So that's all good. Well, this matrix satisfies all 5 conditions. So this matrix is in a reduced echelon form. Great news. Next one. Leading entry, leading entry. Last row doesn't have any leading entries. It's full of zeros, and that row is at the bottom. Good news. Leading entry, zeros below. Leading entry, zeros below. So this is in echelon form. Good news. Let's push it further. Leading entry is 1. Good. Leading entry is 1. Great. So now, last condition. The leading 1 is the only non-zero value in its own column. True. Leading 1 is the only non-zero value in its own column. True, because below him are zeros, above him are zeros. Yes. What happens with the column 2? Nothing, nobody cares. What happens with this column? Nothing, nobody cares. We just care about columns containing leading entries. Hello. So let's check this one. This one is beautiful. This is called identity matrix 4x4. You have diagonal full of zeros, so this matrix has 4 rows, 4 columns. So it's square matrix. And diagonal entries are 1. Beautiful. So obviously it is in reduced echelon form. This one here, identity, again 2x2 this time, in reduced echelon form. How about this one? I have my leading entries. Great, my staircase. So leading entries to the right of each other. This one here has 0 below him, all good. So this is in echelon form already. I see that my leading entries are 1, both of them, that's good news. And now the last check, the leading 1 is the only non-zero value in its own column. True. Leading 1 is the only non-zero value in its own column. True. So this time I have all these properties satisfied, so I have reduced echelon form. Great news. Let's move on. Some examples of cases where I don't have echelon form, no reduced echelon form. So what's wrong with this matrix here? Well, let's see. First row, I have my leading entry, which is here. Good. In column 2, great. Then I hit the second row. Boom, leading entry is here, the first entry here. Wow. So my leading entries are not to the right of each other. Oh, big problem. So this is not in echelon form. My first leading entry is in the column 2, but then I change the row, the leading entry is to the left. That's no good. The definition said, if you want to be in echelon form, your leading entries need to be to the right of each other. Well, here it's not true. So bye-bye, this is not an echelon form. No matter what happens after that, we don't care. This is not an echelon form. Here, what happens? I have my leading entry. In the first row is here. Second row, leading entry off to the left. No good. Leading entry is to the left. Yeah, but I have row of zeros at the bottom. Nobody cares. You violate one of the conditions, you're gone. You violate one of the conditions, you cannot satisfy all the requirements. Bye-bye. So this is not in echelon form. We are sorry. Let's check this one. First row, leading entry here, great. Second row, all zeros. This one is in the middle. Check this one. This one is not row of zeros. So I have a row of zeros in the middle. Well, that's a big problem, because somebody who is in echelon form can never have row of zeros in the middle. Row of zeros need to be at the bottom. If it's not, bye-bye. This matrix is not in echelon form, because I have row of zeros, and row of zeros need to be at the bottom, not in the middle. So goodbye, this is not in echelon form. Big problem. Let's check this one. Leading entry, fine. Next leading entry to the right, fine. Row 3, leading entry below. What's this? So I have first row leading entry is in the left corner, good. Second row leading entry is to the right of the first one, great. Third row leading entry is just below, it's not to the right. It's supposed to be here, not here. So we violate one of the conditions. If we violate one of the conditions, then this is not in echelon form. Goodbye. So this matrix has a problem because the leading entry of the row 3 is not to the right of the leading entry of row 2. Bye-bye. We can do nothing for you. Okay. Something similar happens here. You see, I have leading entry, great. Next leading entry to the right, great. Next leading entry to the right. And then this row, its leading entry is at the beginning. It's to the left. No good. Your leading entry is not at the right place. Sorry. This is not in echelon form. Sorry. Same thing here. Leading entry of the row 4 is just beneath. That's no good. What's wrong here? Well, I have a row of zeros and it is not at the bottom. Well, that's not good news. Sorry, row of zeros, if it is in the matrix, it needs to be at the bottom. Otherwise, your matrix is not in echelon form. What's wrong here? Well, I have my leading entry. Great. And then I hit the row 2. Boof, leading entry is just below. Well, that's no good. Leading entry is supposed to be to the right. So this one violates again a condition. My leading entry of the next row needs to be to the right, but it's not. So if it's not, this matrix is not in echelon form. Ta-da! So those things are very important. That's how we check the conditions. As soon as one of the conditions is violated, goodbye. Matrix is not in echelon form. Now, one of important things to realize is that every matrix, as we saw before, can be transformed. We can apply elementary row operations to it and then get another matrix and get another matrix. Okay, so those matrices are what we call row equivalent matrices, because we apply row elementary operations and then we get from one matrix to another matrix. Great. We can even go back. That's not a problem. Each elementary row operation is invertible. You go one way, but you can go back also to recover. So What we know for now is that every matrix, by proper application of elementary row operations, can be transformed into another matrix that is in echelon form. That's great. The good news is you can have infinitely many echelon forms for each matrix. That's great. But even better news is that each matrix can be transformed into unique reduced echelon form. So I start with my matrix, I apply elementary row operations, and I get different matrix, different matrix, different matrix. At some point, I will reach reduced echelon form. Well, that reduced echelon form is unique for each matrix. So each matrix has unique echelon, reduced echelon form. Okay, so reduced echelon form is something very special for a matrix. By the way, several different matrices could have the same reduced echelon form. That's not a problem. For instance, we will see later that all 4x4 square matrices, when you produce your reduced echelon form, let's say your matrix is invertible, we will see what that means. It has an inverse. So all 4x4 invertible matrices obviously have reduced echelon form, which is identity. So identity 4x4 is a reduced echelon form for all invertible 4x4 matrices. So there are infinitely many of those, and all of them have identities reduced echelon form just because they are invertible. So that's one of the examples. So each matrix has unique reduced echelon form, but that reduced echelon form could be reduced echelon form that you get from different matrices also. So this is cute, nothing special. From your book, their definition is a little bit more rigid. They want you to have a leading one from the day one. I don't want. You can have, for echelon form, you can have any number different from 0 as leading entry. It's fine. Oh, something cute. Matrix 0 is in echelon form. Something very special. Okay, so what happens here? We have, let's say, this example, leading entry, then to the right another leading entry, and then to the right the leading entry again. That's good. So all leading entries are 1, that's bonus. We don't have row of zeros, that's good. Now we check the columns of leading entry. Below the leading entry I have zeros, that's good. Below this leading entry I have zeros, that's good. And below this leading entry there's nothing. Okay, that's also good. So this matrix is in echelon form. But why is it not in reduced echelon form? Well, let's check. I have my leading entry is equal to 1. That's good news. So one of the extra conditions satisfied. Then I check my leading 1. He's the only 0 in his column. Good news. Check leading 1. Well, he is not the only 0 in his column. Below him are zeros, but above it's not 0. Aha. So because of this, this matrix is not in reduced echelon form. So this is just an echelon form, not reduced, just echelon. Sorry. So in your book also they give you different shapes for echelon and reduced echelon forms. So we check here, you can have different numbers, which means you could have non-zero numbers. So that's why this is an echelon form, not reduced, because if I have 7 here, goodbye. One of the conditions is not satisfied. You see I have a row of zeros at the bottom. If I have 2 rows of zeros, they are at the bottom. The column can have zeros, it's not a problem. As an example, it's fine, but normally when we solve linear system, we don't have columns of zeros. That would mean that you have one of the variables that is not needed, which would be a little bit scary for your modeling abilities. And let's say this one here, you have your leading entries to the right, you have 2 rows of zeros at the bottom, your leading entries, below them you have zeros, That's great. And then you check, leading entries are 1 also, and these are the only non-zero values in their columns. So this is in reduced echelon form. And we don't care what are the numbers here. Okay. So this is something that I was talking about. On the right side of this red bar, if you check, you have 4x4 matrix identity. So this is a reduced echelon form. Right? So we had some system to solve, and this system, its reduced echelon form is identity, and you see you have a unique solution for the system. That's beautiful. Again, some examples from your book. On the right side, on the left side of the red bar, if I check this, this is in reduced echelon form. So what's special here? I have 2 rows of zeros there at the bottom. My leading entry is here. That's the only one I need to care about. And it's also equal to 1. That's great. And it's the only non-zero value in its column. So ta-da! This is in reduced echelon form. So let's check this one. Well, this one, its leading entry is here. The next row, its leading entry is to the left. That's no good. This is not an echelon form. Sorry. There's nothing that forces a matrix to be in echelon form. There's nothing wrong. It's just that when we have echelon form, it's cute. So what's wrong with this matrix? Well, my leading entries are to the right. No. The row 3, the leading entry is below the leading entry from row 2. That's no good. This is not echelon form. Bye-bye, sorry. Again, same thing. Okay, what's going on here? Leading entry to the right. Leading entry to the right. Okay, so 1/2, leading entry 1 and 1. Great. So that at least is satisfied. I don't have row of zeros. That's good. Leading entry, zeros below, true. Leading entry, zeros below, true. Leading entry, nothing below, good. So this is in echelon form for sure. Let's see if we can push it to the reduced echelon form. Leading entry 1, great. Leading entry 1, great. Leading entry 1/2, buff. So this doesn't satisfy one of the conditions for reduced echelon form. If you want to have reduced echelon form, you need to have all your leading entries 1, and they are the only non-zero values in their column. Sorry, this is not 1. So this matrix is in echelon form only, just echelon. So let's see what happened here. Some improvement. I have my leading entries equal to 1. That's good. So this is still echelon form. Let's see if we have leading entry, zeros below. Leading entry 0. But this is not the only non-zero value in the column. So again, this matrix is in echelon form, but not reduced. You see, your leading one, he is not the only non-zero value in the column. Sorry. So this is an echelon form, but not reduced. This guy now, it's better. We have third column. My leading one is the only non-zero value. That's good, good progress. And here, sorry, this leading entry, 1, it has a number above him that is different from 0. That's no good. So this matrix is still just an echelon form. We still missed something. So this matrix is only echelon form. Let's push it further. They fixed it, they transformed it, they applied one of the row operations. So now every one, leading one, is the only non-zero value in its column. That's great. So this matrix is in a reduced echelon form. What happens with the column 2? Well, I don't care. It doesn't have leading entry in it, so I don't care. This one, I don't care. It doesn't have a leading entry in it. This one, well, it doesn't have a leading entry. Why do I care? I just care about columns having leading entries. Okay. So I hope you got the idea. So this matrix again is not in echelon form at all. Like, no way. You have your leading entry for the row 2 straight below the leading entry of row 1. Goodbye. Here, situation improved a little bit. I have my leading entry to the right, but then for the row 3, both it's below. That's no good. So it's not in echelon form at all. Obviously, it cannot be in a reduced echelon form either. So what happens with this one? Progress. leading entry, next leading entry to the right. Hey, I have row of zeros in the middle. Oh, that's no good. If I want to have echelon form, I need to have row of zeros at the bottom. So this is no good. So this matrix is not in echelon form at all. This one here, they transformed it, they swapped. Good. So now I have my row of zeros at the bottom at least. Good. So my leading entries are to the right of each other. That's good. The row of zeros at the bottom. That's good. I check my leading entries, and below them there are zeros. Leading entry below zeros. Leading entry below zeros. Great. So this is in echelon form. This matrix is in echelon form. Leading entries are 1. Oh, great. But they are not the only non-zero values in their column. So, sorry, this is only echelon form. It's not reduced. It's just echelon. Let's check the last one. Well, they fixed it by applying other row operations. So now my leading one is the only in the column. My leading one is the only in the column. Everything else is 0. Leading one is the only non-zero value in the column. Great. So this matrix is in reduced echelon form. What happens with the column 2? I don't care. Doesn't have a leading entry. This column, I don't care. Doesn't have a leading entry. This column, I don't care. Doesn't have a leading entry. I just care about columns with leading entries. And when you check the solutions, columns with leading entries, they are associated to the leading variables. Columns that do not have leading entries, they are associated with free variables. That's nice observation. So something similar happens here. I have my reduced echelon form. Great. Everything is done. Row of zeros at the bottom. Leading entries to the right of each other. Leading entries are equal to 1, and they are the only non-zero values in their columns. Reduced echelon form. Yes, sir. This thing here, all good except it's not reduced echelon form. This is just echelon form. Leading entries to the right of each other. Row of 0 at the bottom. Leading entry below him 0. Leading entry below him 0. Leading entry below him 0. Echelon form, great. Leading entries are 1. Oh, we make some progress. But that's not the only non-zero value in the column. Sorry. So this is only echelon form. It is not reduced. It's just echelon. This one also, it's just echelon for the same reasons. Here, this matrix has row of zeros at the bottom, good news, but the leading entry of the row 2 is beneath leading entry of row 1. That's no good. This guy is supposed to be on the other side, to the right, but it's not. So this matrix is not in echelon form at all. Okay, so when you are asked, is this matrix in echelon form or reduced echelon form or neither? Well, you just need to figure out what is the situation. Nobody's asking you to transform it, just asking, is it? Answer is yes or no. Okay, so that's pretty much about echelon form, reduced echelon form. We need to be able to recognize these when we see them, because it will simplify our life. One of the reasons is when you are solving your linear system, your Gauss-Jordan procedure will stop when you reach reduced echelon form, and that's gonna give you a way to compute the solution. So that's why it is important to recognize a matrix in reduced echelon form. It helps you stop your Gauss-Jordan algorithm, so you don't compute till you die. Alright, so that's it. I hope you understood. You need to practice. It's pretty visual. Practice, practice, practice.